Alright guys, so let's go ahead and go over your study guide here. Let's take a look. The table below gives selected values for the function f of x. So what is the limit of f of x as x approaches 3 from the left? So this is where we are approaching 3 from the left, and we want to know what's the limit of f, which is the y value there. So what y value are we approaching from the left? Well, it's 0.16, 0.1669, 0.1666, and so I think it's safe to say that the y value we're approaching is probably 0.16 with a bar on the top of it. It's just going to be getting closer and closer to 0.66666, okay? And I would say the same thing is happening here on the right. It's 0.1639, 0.1664, 0.1666, and then, so, same thing. Boom. And since the limit on the left and the right are the same, we can say, okay, well, that's just what the limit is. Now, what is f of 3? In other words, what is the value of the function at x equals 3? Well, that's actually undefined. The function doesn't exist there. Remember, that's the difference between this expression and these three expressions. The first three expressions are about what it's approaching. It's approaching 0.16 bar, but does it ever actually get to equal it? No, it's undefined. So that's the difference for part D. All right, part E. Is this now, oh, by the way, thinking of this as a graph then, since I would encourage you guys to write this on your paper. Since we are approaching the same point on the left and on the right, but it doesn't exist, this is what we call a hole. Okay? So I would make that note on here. So basically, since what we're approaching from the left and the right is the same, but the point actually doesn't exist, that's what we call a hole. Okay? And that's going to help us with one of these questions here. Is this function continuous or discontinuous at x equals 3? Well, it's discontinuous. And I've given you guys 3 reasons why a function may be discontinuous. One is because the limit doesn't exist, one is because the function doesn't exist, and the last one is because even though both of those things may exist, they're not equal to each other. In this case, the fact is that the function doesn't exist. Okay? So there's that. And which of the following best characterizes this function at x equals 3? As I've already said to you, it has a hole on it. All right, let's go ahead and continue our journey here. Number 2. The table below gives selected values of g of x. All right, so now we want to approach 0 from the left. We want to ask ourselves, what y value are we approaching? And this should say g, by the way. Well, 1.9, 1.99, 1.999999. Now, some of you guys might think you could put 1.9 bar, but whenever you have a 9 bar, that means basically it's just going to be 2. Okay, you can't do that with other numbers. When it's a 9, that basically just means it's approaching 2. Okay, the next number up. How about on the other side as we approach 0 from the right? The y value goes from negative 3.5, negative 3.02, negative 3.001, and then, oh, we stopped there in the middle there. All right, well, it looks like it's approaching negative 3 from the right. So what is the limit then of this function at 0? Well, it doesn't exist because the limit from the left and the limit from the right are not the same. What is g of negative 3? Well, this time it's actually defined. The answer, this is supposed to be 0. What is g of 0? Sorry about that. What is g of 0? Well, g of 0 is negative 3. Is this function continuous or discontinuous at 0? And the answer is it is discontinuous. Now, this time it's not discontinuous because the function doesn't exist, because it does. It's discontinuous because the limit does not exist. Now, which of the following best characterizes this function x equals 0? Well, as I'm approaching 0 from the left, I'm approaching a value of 2. And as I'm approaching 0 from the right, I'm approaching a value of -3. So that's actually going to be down here. So they're not meeting at a common point. And whenever that happens, we have a jump on our hands. So this is an example of a jump. So anytime the limit from the left and the right are not the same, then you have a jump discontinuity. All right, let's go ahead and take a look at another one here. The table below gives selected values of h of x. Once again, my document's wrong. That's supposed to say h there. All right, so what is the limit of the h function as x approaches -2 from the left? So once again, we're coming at it from here. We want to know what's y value. Well, it's not getting closer to anything because as you guys can see, the distance between each number set is not getting smaller and smaller and smaller. It's getting bigger and bigger and bigger. And when that happens, you're going off into infinity. Now the same thing is happening as we approach -2 from the right, only it's negative values, so they're becoming more and more negative. So in this case we have positive infinity and we have negative infinity from the right. So from the left it's positive infinity, from the right it's negative infinity. So what's the limit? It just doesn't exist. Now let's just say all three y values on this right side were positive. So let's just change all these to positives. What would be the value of the limit now? Well, even though it still doesn't exist, if both the right and left-handed limits were positive, which is what that would be if you change those three numbers to positives, then that would mean that we wouldn't put d and e. That would mean we'd put infinity. Okay, so there's that. Now, what is the value of h of -2? Once again, it's undefined. The function does not exist at that point. So is it continuous or discontinuous? The answer is it's discontinuous. Now, you actually can say two different things here. You could say either h of 2 is undefined or does not exist, or you could just say that the limit of this function as x approaches 2 does not exist, because neither one of them exists. So it doesn't matter. You don't have to say both. You could just say one of them, but the point is there it doesn't exist. Now, which of the following best characterizes this function at x equals -2? Well, here's what's happening. As I'm approaching -2, the y values are getting bigger and bigger and bigger on the right side. So as I approach, it's just shooting up high from the left. Now, as I approach from the right, they're becoming more and more negative. And when you have a situation like that, that's a characteristic of a vertical asymptote. So part G is an example of a vertical asymptote. All right. Moving on, let's take a look at yet another. The table below gives selected values for j of x this time, and once again, this is supposed to say j. All right. The limit j of x as x approaches 1. All right, now notice this time I'm not going to be approaching from the left or the right, but I am, really. It doesn't tell me to do that, but whenever they don't give you a plus or a minus here, that means do both. So left and right. From the left, it looks like I'm getting closer and closer to 3, and from the right, it looks like I'm getting closer and closer to 3. And so, as you guys can see, since it's the same on the left and the right, we can go ahead and say that the limit is 3. And what is j of 1? Well, it's 3. Is this function continuous or discontinuous? This function is continuous. This is the only one that was continuous. Why is it continuous? Because the limit as x approached 1 existed, and the value of the function, let me back up actually, make sure I put the right letter here. This was supposed to be j. The limit of the function existed, and the value of the function existed, and they were both 3, so they're both equal to each other. So here's my reason. You do need to be able to explain your reason. Which of the following best characterizes this function at x equals 3? Well, it doesn't have a hole, a jump, or an asymptote because it's continuous. And so whenever you have a continuous one, we're just going to say, okay, it's continuous. All right. So that's the table stuff you guys can expect to see. Let's go ahead and move on into some graphing things here. All right. Now with these ones, guys, you got to pay close attention to what function we are working with. So for this one, I'm looking at function k. So I'm going to be on this picture here. And I'm approaching 1 from the left. So you got to pay close attention to all the written details there. You don't want to be doing it on the wrong picture, otherwise you're going to get the wrong answer, right? So I want to approach 1 from the left. Now 1 from the left is right here. So if I'm approaching 1 from the left, I'm going to land at this spot here, and the limit is the y value at that point. And the y value at that point is 1. What if I approached 1 from the right for part B? That's what the little plus means there. So now I'm going to approach 1 from the right. Now if I'm approaching 1 from the right, x equals 1, then I'm now landing at this spot. And that y value, I would estimate that to be about negative 0.5. So what's the limit? Well, it doesn't exist, because the limit from the left and the right are not the same. We have a jump discontinuity there, so the limit does not exist. But what is k of 1? Well, k of 1 is where the solid dot's at. And this is my solid dot. And so k of 1 is the y value at that point, which is 1. All right, so that's number 5. Let's go ahead and take a look at number 6. For number 6, we're still on the k function, so I still want to be looking at this same picture here. But now we're going to be approaching 3 from the left, 3 from the right. So let's go ahead and do those one at a time. So 3 from the left would be this. And as you can see, that's one that's going on up into infinity, because it's going in an upward direction. And if I'm approaching 3 from the right, the picture kind of stops there, but we can assume that it just keeps going in a downward fashion like that. So that one's going to be negative infinity. And therefore, we would just say that this limit does not exist. And remember, if they were both the same sign, then instead of saying d and e here, we would put an infinity symbol if we could. But in this case, they're opposite signs from the left and right. For the total limit there on part C, we just say does not exist. What is k of 3? Well, that's a vertical asymptote, you guys. So anytime you have a vertical asymptote, the function doesn't exist there either. There is no y value, so we'll say does not exist. All right, let's go ahead and take a look at number 7. Now notice we're switching functions here. So now I'm going to be on the m function. So that would be this guy here. And we're approaching negative 2 from the left for part A. So negative 2 from the left. Well, here's where the function equals negative 2. And if I'm approaching that from the left, I get a y value of 1. And if I approach negative 2 from the right, I land at actually the same exact y value. It's 1. And therefore, the limit exists. And it's 1. When the limit from the left and the right are the same, then that means the limit is 1. What is m of 2? In other words, what's the y value at that point? Well, it just so happens to be the same spot, so it's 1. That's an example of a continuous function, because it's the same from the left as it is from the right, so the limit exists, and the solid dot is where they meet at. And that means it's a continuous point, a point of continuity. All right, let's go ahead and take a look at number 8. Number 8. Here we're practicing with the properties of limits. Okay, so I have 2 times k of x plus m of x over k of x squared, and I want to find the limit of this entire expression as x approaches negative 2. Now, I don't want to confuse you guys by writing this out in a bunch of detail. So basically, all we're going to do is I'm just going to say take the limit of k and put it there. Take the limit of m as x approaches negative 2 and put it there. And take the limit of k as x approaches negative 2 again and put it there. So let's first of all find what is the limit of k as x approaches negative 2. Well, here's negative 2. And the limit there would be it's 2. Okay? So the value of my k function as I approach negative 2 is 2. So that and that are going to be replaced with 2's. I'll color them in. And then we have our plus the m of x function there. plus the m of x function. Well, I also want to take the limit of my m of x function as x approaches negative 2. So we've already got that one as well earlier. That point was 1. So that's going to be a 1. So basically just find the limit of each of the functions at this particular value of x, plug it in, and then evaluate from there just using standard order of operations. So I have 4 plus 1, which is 5 over 4. So the answer to this question here on 8a is 5/4. All right, let's go ahead and take a look at part B for number 8. So for part B, what we're going to do is we're going to take this limit and we're going to slide it to the inside function so it looks like this. And we're going to evaluate this limit first. So what is the limit of k of x? So we're at this function over here. What's the limit of k of x as x approaches 4? From the left and from the right, we're meeting at the same point. It's an open dot, but that doesn't matter. We're still approaching the same spot on both sides. And that open dot has a y value of negative 2. So that means we're looking for a y value of negative 2. And so now I'm going to come over here to my m graph, and I'm going to find what is the m's value at negative 2? Well, we already know that from earlier. Also, it's 1. So the answer to part B would be 1. Let's take a look at part C. Now, one-sided limits with composite functions. This is what a composite function is when you have a function inside of a function. One-sided limits, like this one here, where there's a little plus or a minus in the corner, with composite functions, a little bit trickier. Okay, we're still going to start like we did on part B by applying the limit to the inner function there. So that would look like this. So I want to find the limit of m of x as x approaches negative 1 from the left. So I'm on m of x. I'm approaching negative 1 from the left. And I'm approaching a y value of 0. But here's the deal, though. I'm going to put a 0 here. But since it's a one-sided limit, that means as I'm approaching 0 from the left, I have to think about the y values here. I'm approaching that y value of 0 from above 0, which means that I'm approaching this y value of 0 from y values that are greater than 0. So I'm going to put a little plus there. So now that means when I switch over here to the k of x function to answer this part of what is k of 0 with a little plus there, that means I'm going to approach 0 from the right, since it's a positive, and now the 0 is going to act not like a y anymore, now it's going to act like an x. So I'm approaching an x value of 0 from numbers that are bigger than 0, and when you're talking about x, that means from the right. So I want to approach 0 from the right. So if I do that on the k function, I'm going to land right here at this value, which is a negative 1. So the answer to part C is negative 1. Let's do another one like that. We have another composite function with a one-sided limit. So it's going to be similar. So first thing we do is we take the limit and we apply it to the inner function there. So I want to approach negative 2 from the right on the m function. So here's the m function. And if I approach negative 2 from the right, then I'm approaching a y value of 1. But since we're doing one-sided limits, I have to think about where I'm coming from. Since I'm coming at it from the right, I'm also coming at it from underneath of that dot, which means that I'm approaching a y value of 1 from y values that are actually less than 1. So now when I try to evaluate this by going over to the k graph, I have to think in terms of x. So I'm approaching an x value of 1 from values of x that are less than 1. And whenever you're talking about less than on the x-axis, that's from the left. So I'm approaching 1 from the left on the k function. So here's my value of 1. and I'm approaching it from the left, and I land at a y value there of a positive 1. All right, let's take a look at part E. This one is not a one-sided limit, so let's go ahead and apply it to the inside function there. What is the limit of the m of x function as x approaches 2? Now, in order for this to work, that limit actually has to exist. And it does. From the left and from the right, they're both approaching 2 from the same value there. And so we end up with an output value of 1. And so now what we need to do is just find out what is k of 1. So in this case, we are approaching both from the left and from the right. You notice how both of those directions are above the dot. So we're coming at that 1 from above. Okay? And so in this case, if I'm coming at, oops, that's incorrect, sorry. If I'm approaching 1 from above, when I think of it as a y value, when I think of it as an x value, I'm approaching 1 from the right. So for the graph over here on k, I'm approaching the 1 from the right, which will put me at a y value of about negative 0.5. Okay? Now, if you ever had a situation where you were approaching your m of x function and they were not both coming from above, but one was coming from above and one was coming from below, then whenever you come over here on your k graph, you would have to approach from both directions. If they didn't meet at the same spot, you would just say it doesn't exist. Let's go ahead and take a look at number 9 here. So now we're going to look at the n function. As you guys can see, we're approaching 1 from the left. 1 from the left. So if I'm approaching 1 from the left, that's what this would look like here. So that's a negative infinity. And if I'm approaching 1 from the right, that's a positive infinity. And once again, since the signs don't match from the left and right, we're just going to say it does not exist for the final limit there. Part D. This is both of these were what we call infinite limits, but part D is what we call a limit at infinity. So we want to find the limit of n as x approaches positive infinity. Now that means we're going to be going to the right. So what y value do we reach as we go to the right forever? So as I go to the right forever, just going to keep going. What y value do I seem to be getting closer and closer to? Well, I get closer and closer to the y value of this dotted line, which is 4. All right, let's take a look at part E here. On part E, we have a composite function with a one-sided limit. So we have n of the limit as x approaches 3 from the right of k of x. So if I'm approaching 3 from the right on the k function, let's see what that looks like. Well, that would be this. I'm going down here forever, and so I'm approaching negative infinity. Now, what does this mean? Well, this means that I'm going to, now instead of thinking of this as a y value, now we're going to switch over and start, as we switch over here to the n graph, it becomes an x value, because now it's an input, right? So we're going to infinity, but a negative infinity. Now, since this is an x value at this point, that means we're going to go to the left forever. So if I go to the left forever, I still approach that same y value of 4. It's not too uncommon. It's not always the case, but a lot of times horizontal asymptotes are the same on the left and the right like that. Okay, so there's some essential things. Let's go ahead and take a look at some of these other questions here. Got to zoom out a little bit. All right, number 10. Is k of x continuous at x equals 1 Explain why or why not. Well, that's where k of x equals 1. So no, the answer is no. That's a jump discontinuity, but that we're not going to explain it that way, okay? We're going to say no. And when you have a jump discontinuity, that means the limit does not exist. Now, when you're writing these out, you guys, it's important that you use the right numbers and letters here. So, for instance, you have to put a k of x here. Don't forget and accidentally put an f of x. And then also, you need to make sure you have the right number here. We're approaching 1. So, no, since the limit of k of x as x approaches 1 does not exist. That would be our answer to number 10. Let's take a look at 11. Is k of x continuous at 3? Well, 3 was where we had that vertical asymptote, and once again, that's a no. And you could say two different answers there. You could say because k of 3 is not defined, or you could also say that the limit of k of x as x approaches 3 is not defined or does not exist. Okay, when you have a vertical asymptote, neither the limit nor the y value exist at that point. Let's go ahead and take a look at number 12. Is k of x continuous at x equals 4? And the answer is no. We have a hole there. So why, though? The limit exists, but when you have a hole, that means the function doesn't exist. So k of 4 does not exist. Next question. Is m of x continuous at x equals -2? And we figured that out earlier. The answer was yes, but we have to explain why now, right? And the reason is because m of -2 exists, and the limit of m of x as x approaches -2 exists, and they're the same. And so this is our explanation for that. All right. Number 14. Which limits from numbers 8 through 12 above are infinite limits? So an infinite limit is one where the y value is infinity, and it could be plus or minus. So one where the y value is positive or negative infinity. So basically you have to look at your answers. So for numbers 6a through c, these were all infinity answers in case you guys forgot. So those are examples of infinite limits. What else was an infinite limit up here? I believe we also had some infinite limits here. Here the answers were infinity as well. So you could say 9a and b, like so. Okay. Now technically, I think you can also call this one an infinite limit in a way, because the limit of k of x as x approaches 3 from the right was an infinite limit. It didn't give us infinity as an answer, so that was debatable, but I won't be asking you guys a question like to tell me if that's an infinite limit or not on a test, so you don't have to worry about it. I was just kind of caught my attention, honestly. I think we'll just stick with the ones that strictly have infinities as answers. Let's go ahead and take a look at number 16, or 15, I mean. For which limits from numbers 8 through 12 above are limits at infinity? Okay, so those are ones where the x itself is approaching infinity. Now, we only have one of those up here from what I can discern. It's right here. Once again, technically you could say that this is a limit at infinity, because when we put the limit in here, that was an infinite limit. But after you take that infinite limit and you plug it into the n, remember how we had this? Well, now basically what you were doing is we were finding the limit of n at a negative infinity. So technically that is a limit at infinity also. But once again, that's a little ambiguous and weird, so I'm not going to worry about it. 9D is good enough. Number 16. Give all values of x for which m of x has a jump discontinuity. Well, I see a jump here. A jump is any time the limit from the left and the right are not the same. Or in other words, 2 points with the same x value but different y values, right? vertical to each other. So that's a jump. So we have -1. We also have a jump right here at +1. All right, let's go ahead and move along a little bit. For this last section here, you guys, you're probably going to want to get out that piece of paper I gave you guys a while back that gave you some information about describing the continuity and discontinuity of common functions. So I'll go ahead and zoom in here a little bit. All right, so the first one we're being asked, identify the points of discontinuity for each function. So the first thing you got to do is look at the function. Here we're dealing with a cotangent function. So I'm going to go to my little sheet here of continuity of common functions. I'm going to find cotangent. It's right here. And where is cotangent discontinuous? That would be the last column here. So for cotangent, it's discontinuous for all x for which a of x, the argument, the part inside parentheses, is equal to n pi. So here's my a of x. So it's discontinuous for all x for which (2x) is equal to n times pi. And all we have to do at this point is just divide both sides by 2 and specify that n represents any integer. Now, if you don't know what this means, that's not good. You should. We talked about it earlier, but I'll restate what that means. N is an integer like 1, 2, 3, 4, 5, 6, or -1, -2, -3, -4, -5, -6. So, for instance, there would be a discontinuity at 1 pi over 2, or there would be a discontinuity at -1 pi over 2, or there would be a discontinuity at 3 pi over 2, or -3 pi over 2, or even 2 pi over 2. Which you guys know just reduces to pi, or at -2 pi over 2, which you guys know just reduces to -pi. So any integer value. And so basically with a cotangent function that looks something like this, you just have these vertical asymptotes where there's discontinuities, and these are all the places where those discontinuities would exist for this particular cotangent function. Okay? All right, let's go ahead and take a look at the next one here. Where are the discontinuities for cosine? Well, if you look at your sheet, there are none. Cosine does not have any discontinuities, so we're good. Same thing with number 19. This is a polynomial. Polynomials also have no discontinuities. And guess what? Same thing for number 20. There are no discontinuities for exponential functions. Now, number 21, though, is a different story. That's a rational function. Rational functions, or quotient functions, do have discontinuities. So let's take a look at them real quick here. Here's a rational function. So rational functions look like a fraction, right? And the discontinuities exist for all x for which the denominator, d of x, equals 0. Okay? So let's go back over here. And we'll say, okay, cool. So what's my denominator? It's x minus 8. So, discontinuous for all x for which x minus 8 equals 0. Or you could just solve for x by adding 8 on both sides, which is x equals 8. And that's it. Discontinuous for all x for which x minus 8 equals 0, or in other words, x cannot equal 8. So there it is. That's the only point of discontinuity for a rational function. All right, now I'm going to do the flip side of this question here for numbers 22 and 23. For square root functions and natural log functions, instead of asking where they're discontinuous because they really don't have any discontinuities, it's better just to ask, well, where are they continuous? Because Once those functions start, they never have discontinuities, but they do start at a specific spot. So how do you find out where they're continuous? Well, when you're on your little sheet here, instead of looking at the last column, which tells you where the discontinuities are, you look at the second to last column, which tells you where it's continuous. So for number 22 there, we're looking at a square root function. A square root function. And that's a radical function with an even root, like this one here. And those are continuous for all x for which the radicand is positive, or greater than or equal to 0. So, going back to my thing here then, this function would be continuous for all x for which the radicand, 4 minus x, is greater than or equal to 0. Now, if we actually solve for this, though, minus 4 on both sides, right? You got to be careful here. Divide by a negative 1. Little algebra trick you got to remember. If you divide by a negative, you need to reverse your inequality. So the final answer here is x is less than or equal to positive 4. Okay? So it's continuous for all x for which x is less than or equal to 4. But remember, you only flip that inequality if you're dividing by a negative. If you divide by a positive number, you wouldn't do that. Okay? So whatever number you're putting in the denominator there, if it's positive, you don't flip it. If it's negative, you do flip it. All right, let's go ahead and take a look at number 23. Number 23 is a natural log function, and we want to know where is that one continuous. So once again, we come back to our sheet, we find logarithms, and that's what they look like. And they are continuous for all x for which the argument, which is the part inside the parentheses there, is greater than 0, but not equal to, just greater than. Unlike radical functions, they can't actually equal 0. They have to be greater than 0 only. So in this case, we would say this function here is continuous for all x for which x plus 4 is greater than 0. And if we minus the 4 on both sides, we end up with x being greater than negative 4. Okay? And so there is our final answer there. And so that's your study guide. Hopefully it was helpful to you guys, and good luck on your quiz tomorrow.